Let's run through complete solutions to the next 4 calculator multiple choice problems in our series from the 2012 released AP Calculus A/B exam. Now, as I said, these are calculator active problems, so make sure you have your calculator beside you so you can follow along. Let's dive in. So this first problem, number 80, is a classic AP setup. We're given some information and we're asked to figure out which of the following 3 statements are true. And then we pick which we find to be true from the 5 possible choices they've given us. The way into approaching these is just take each statement in turn and figure out if it's true. So we're given the graph f prime of a function f and we're asked some information about f. So we're asked about what's happening at x equals -3. So that is there on the graph. We're asked about what's happening at x equals -2. That's there. And then we're asked about this range, this interval from 0 up to 4. So those are where we're looking on the graph of f prime to try and learn something about f. Well, first things first, I am looking for if there's a relative minimum at x equals -3 for the function f. Well, notice at x equals -3, f prime is starts off below the x-axis, so f prime is negative, and then it transitions to being above the x-axis, so f prime becomes positive. Now that very much controls the relative min-max behavior of the function f. If we think about what that looks like for the function, well, at -3, I don't really know what the function is doing, but I know that I start off with f prime being negative, so my tangents are sloping downwards, and then f prime becomes positive on the other side of x equals -3, so my tangents start sloping upwards, so my graph of f is going to look something like this. So yes, indeed, we are expecting there to be a relative minimum for f at x equals -3. So statement number 1 is for sure true. Let's move on to the second statement. So we are looking for, is there an inflection point at x equals -2? And we need to deduce this from the graph of f prime. Well, an inflection point, hopefully we'll remember, occurs where concavity changes sign. So concavity changes sign at an inflection point. That's how we detect it. And so that means I need f double prime to change sign. The concavity of a function is detected by the sign of the second derivative f double prime. So if concavity is changing from up or down to up, the sign of f double prime had better change. Well, if we look at what's going on here in the graph, well, nearby x equals -2, f prime is increasing. Okay. F prime is increasing nearby x equals -2. And so that means, because the second derivative is the derivative of f prime, increasing behavior means that f double prime is positive. So concavity can't change to give us an inflection point at x equals -2 because the second derivative is constantly positive. Okay. It does not change sign, so I cannot have a point of inflection there. So the second statement is not true. So if you look at our answer choices, I know it's either going to be A or E at this point, because 1 is certainly true, and 2 is not true. I just don't know if 3 is true or not, so let's figure that out. The third statement is saying the graph of f is concave down on the interval 0 up to 4. Well, we've already talked about how concavity is detected by the second derivative f double prime. So to detect that concave down is occurring, that just means f double prime is negative. Okay, that's how we detect concavity, using this being concave down with the second derivative. F double prime should be negative. Is f double prime negative when x is between 0 and 4? Well, the function is decreasing the whole time, isn't it? F prime is decreasing. So that tells me its derivative, f double prime, must be negative. So indeed, I have verified on the interval 0 up to 4, f double prime is negative, and so indeed the graph of f will be concave down on that interval, and so statement number 3 is true. So looking at my answer choices, I see that means the correct answer is choice E. Good job. This next problem, 81, is a word problem, and if we read through what it's saying water's being pumped into a tank. We're given the rate at which it's pumped in using this function, r of t. We know there are 800 gallons at the start, and we want to know how much water there is after 20 minutes. There's a lot going on contextually in this problem, but if we strip it all back, what this is really asking us to do is apply our net change theorem. Because we have a rate, and we want to know how much stuff is added or removed, in this case, added over some stretch of time. So the net change theorem says we're supposed to start with whatever our initial quantity was. In this case, it was 800. To figure out what the net change is, I add on an integral. So I'm going to integrate the rate, r of t, with respect to t, and my interval over which I'm going to integrate is the first 20 minutes, from 0 up to 20. So the great thing is we have this rule for r of t, so we can grab our calculator and calculate that definite integral using our calculator. Now, if you're not super confident at using your calculator, where I would direct you right now is my calculator skills video. I'll put a link in the description underneath, and I'll put a link in the description down below, and and in that video, I run through the 4 calculator skills that you absolutely need to know for your AP Calculus exam. They come up every year. If you can do those, you're going to be in great shape. Here, we're going to carry out one of those skills, namely calculating a definite integral. So I'm going to pull up my calculator app and type in, okay, I want to do 800, and then I'm going to add on this definite integral. How do we do this on our calculator? We're going to pull up the math menu, and then we're going to hit option 9, fn int, to carry out my integral. Okay, and I need to fill in the boxes here. So I'm doing the integral from 0 up to 20 of my rule. Now, on your physical calculator, you can change your variable if you want. I would just stick with x. If you want to make it t, you sure can, but then you've got to mess about with the alpha button. Just not worth it. So let's write this as 30 times, open parentheses, 1 minus e to the power of negative 0.16 times my variable, and then we are done. So what do I get? Ah, okay. So it is, to the nearest gallon, it is 1,220. Okay. Is that one of our answer choices? It is indeed. It is option D. So that is the answer that our calculator gave us. Amazing. Answer D. Next question, problem 82, is giving us an expression for the derivative f prime and asking us to deduce if f has a local maximum. This is a little bit like that analysis we did in the very first problem, but here it's truly focused on this one statement. Where do we have this local maximum occurring? And unlike in the first problem, we are going to need our calculator here. So I'm going to draw a similar setup like we did in the first problem, though. If we're looking for a local maximum, okay, that means I want it to look something like this. The graph of f should look something like that. So in particular, on the left, I should have f prime being positive because I want the function to be sloping upwards. And on the right, I should have f prime being negative because I want the function to be sloping, the graph of the function to be sloping downwards. Well, I can find where this happens on my calculator for this f prime. So I need to find where f prime changes from positive to negative. So as I go along the x-axis that way, I need to find where f prime changes from being above the x-axis to below the x-axis. Let's pull up our calculator. So I'll go to my y equals window so that I can enter the rule for the function, and it is simply the square root of x to the 4th power plus 1 plus x cubed minus 3x. Not entirely sure what my window's set to. Let's just have a look. Ah, okay. That's not too bad of a window. Okay, if you did it on your physical calculator, take a wee second to draw that out for you. But here, this is what we have. I'm going to want to zoom in maybe a little bit just to identify the features a little bit. There we go. So I want to see where on this graph f prime is changing from positive to negative, going from above the x-axis to below the x-axis. I see that happens exactly one place. It crosses the x-axis 3 times, and it is crossing from above to below at this x value a little bit less than 0.5. So we can already estimate that it's going to be answer choice C, right? Because that is the only positive option that's slightly less than 0.5. But since we're here, let's actually do the calculation using the calculator just to double check. If we were crunched for time on the actual exam, maybe we would be happy with that conclusion. But we're going to hit second trace to pull up the calculate menu. I'm going to hit option 2 to give me my 0. Now I need to sandwich the x-intercept I'm interested in. So let's say there's my left bound. Here is my right bound. And then you'll hit enter one more time to make a guess. And you can see, yes, 2 3 decimal places. The x-intercept occurs at x equals 0.350. Which, fortunately for us, is indeed answer choice C. Good job. Okay, final problem of the video, number 83. And in this problem, we're given the graph of a velocity of a car as it comes to rest over 8 seconds. You can see at t equals 8 in the graph, the velocity has dropped to 0. And we're asked to estimate the distance that the car has traveled between t equals 0 and that resting point at t equals 8. So the distance traveled is going to be an integral, right? If I integrate speed, I get distance. But notice in this problem, because the velocity is always positive, velocity and the speed are the same in this case. Velocity usually cares about sign, positive, negative, but here, because velocity is always positive, we can work with it as speed. So this would be how I would calculate the distance traveled. Distance is the integral of speed. Displacement is the integral of velocity. I put in my endpoint 0 and 8. But here I don't have a rule for v of t, so I can't use my calculator to plug in the integral and figure out the value of this definite integral, the distance traveled. But I do have a graph, and what we need to remember is, by definition, this definite integral is the area under the graph of this velocity curve. Well, what if we just count boxes, right? Seems kind of dumb, but if we're just looking for the best estimate, that might be a pretty good estimate when I don't really have anything else to go on. So we've decided we're going to estimate the area under this graph by counting boxes. Well, notice the area of each box is just 10, because base is 1, height is 10. So let's start by counting the actual number of complete boxes that we have. I'm going to count that one as complete, even though it's missing a tiny clipped corner. And so on, so on. Okay, those are all of my complete boxes. Great. So what do I have? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's at least 160 feet, 16 times 10 of area under this graph. I've counted sort of this area. Oops. I've counted this area here. Is that area that I've counted as 160? Is it going to be, when I add in those extra pieces, am I going to get up to 180, 210, or 260? That's the remainder of the question. Because I can estimate better than just 160, right? Because I can do some more counting of these areas that are left over. And the key here is I can kind of jigsaw together some of these pieces into complete squares. I'm going to show you what I mean. So if we take this partial square, it kind of jigsaws together nicely. If I took these two jigsaw pieces and fit them together, they would kind of make a complete square. Maybe not perfectly, but pretty nicely. And you can see I can do this with a few other pairs as well. So I have, here, this almost complete square pairs together pretty nicely with this little corner to give me a complete square. Its neighbor does pretty well too. Okay, I've got this one, which partners together nicely with that little square. Maybe not perfectly, but it gives me a complete square together. What do I have then? Well, I've got this guy partnering up with this guy. And those will maybe a little bit less than one complete square. And I've now got one pair left. What color haven't I used? Let's use this color. Okay, we got this one. And okay, if I pair it with that, it's maybe a little bit larger than a square. But let's see what we had. So we had those 16 squares to begin with. And what have I added by my jigsawing together? I've got this pair, 1, this pair, 2, this pair, 3, this pair, 4, and this pair, 5. So that's 16 plus 5 extra squares I was able to find. So that is 21 total boxes, and each box had an area of 10. So that means the total area under the curve is 210 feet. Is that one of my answer choices? Thank goodness it is. Yes. So part D is the correct, or choice D is the correct answer. Okay, there we have it. The next 4 calculator multiple choice problems from the 2012 exam. Let me know in the comments how you got on. Which one did you think was the trickiest? I didn't love that last one with counting all those boxes, but sometimes that's what you've got to do. Notice only 2 of the 4 problems actually required us to use our calculator. That's sometimes how it goes. Just as a reminder, I will put a link to the calculator skills video down in the comments, and if you want to practice more multiple choice problems, calculator or not, I'll put a link to the playlist here. Apart from that, I look forward to seeing you in the next video. Bye!